Okay, a few equation solving techniques. Now this is not a comprehensive list. Incidentally, you can access more explanation on where these videos come from because this is somewhat out of context, the context being the context of the course here or at the 1905-02 assignment page if you're using the course assignment page. Okay. So, equation solving techniques. Again, not comprehensive, but a few techniques, a few things that I find people tend to forget, tend not to use, or tend to use wrong. Okay, so multiplied by a common denominator, that occurs like when you have denominators. Anytime you have denominators, you find a common denominator and multiply both sides by the common denominator. In this case, the common denominator would be x minus 5 times x minus 2. So you multiply both sides by x minus 5 times x minus 2. It'll give you x minus 5 times x minus 2 over 1 over x minus 5 plus x minus 5 times x minus 2 times 3, where I've taken the liberty of using the distributive law to multiply this quantity by the two terms on this side. And that's going to be x minus 5 times x minus 2 times 5 over x minus 2. Okay, so this term simplifies. X minus 5 will divide x minus 5, giving you 1, leaving you with just x minus 2. I don't like the C word. I don't like to cross things out because people do it wrong and can't be persuaded to do it right. Okay, we multiply this out. The product here will be x squared minus 7x plus 10, and you multiply that by 3, and I believe you're going to get 3x squared minus 21x plus 30. And over on this side, the x minus 2 divides the x minus 2. The x minus 5 will be written multiplied by 5, so you're going to get 5x minus 5. Now what kind of equation do we have here? We talked previously about identifying equations. This is a quadratic equation. You just bring every term over onto the left, and if I do the arithmetic correctly, which is always doubtful, I get the 3x squared. I'm going to have a negative 5x with a negative 21x, giving me negative 26x. Adding an x gives me minus 25x plus 30. And now I can use the quadratic formula, or I can attempt to factor this. And since I'm here, I'm going to move over to the zero property, because to solve this by factoring, you have to use the zero property. It's supposed to be an R, it looks like an N. Okay? So, if I have this equation, and then we'll come back to what that says about this one, how am I going to solve it? Well, the only possible solutions come about if this is 0, this factor here, or this factor is 0, or this factor is 0. So we can say that, okay, the only solutions are the solutions to this, which is easy to solve, or this. Okay? Well, this one can be solved, and actually we could use a quadratic formula, but I believe we can solve it by factoring. And this illustrates how we would solve a quadratic by factoring, okay? Now, how can this be 0? Well, this has to be 0, or this has to be 0. So x plus 6 equals 0, or x minus 1 equals 0. Or, well, x minus 2 equals 0, x equals 2. And now, what about x squared plus x plus 5 equals 0? Well, I'm not going to do the substitution, but the discriminant is negative. The thing under the radical in the quadratic formula is going to be negative 24, and you can check that out. The discriminant b squared minus 4ac from the quadratic formula is, and I said negative 24, it's negative 19. I'm squaring the 5 instead of multiplying it by 4, okay? And there's no real solution. Now you would have a couple of complex solutions, and if you were looking for solutions of this equation over the complex numbers, you could well want to include the complex solution here. But if we're doing real solutions, for example, to graph the function in a two-dimensional graph, we would discard this. Okay, so no real solution here. Now this solution is x equals 6, this is x equals 1. Or, quoting from both here, x equals 2. So x equals negative 6, or x equals 1, or x equals 2. Those are the only possible solutions. And of course then, if you're going to graph this, now you know where the zeros of this function are. It'll be 0 at negative 6, it'll be 0 at 1, it'll be 0 at 2. You partition the x-axis into 4 subintervals, 2 of them being infinite, and determine whether this is positive or negative in each, and you do some other things, and you get the graph. Just reminding you of that because we're going to talk about that. Okay, so over here, again, you can use a quadratic formula. If you use factoring, you use the zero property. And that's one reason that the common error of, like, if you have x plus 6 times x minus 1 equals 5, and then you factor this, and then you say x plus 6 is 5, or x minus 1 is 5, or whatever, that doesn't work. It's only if this product is 0, you can conclude that this is 0 or this is 0. That's it. Okay. If you got an even power of the variable, you reduce an equation by one means or another to x squared equals 7/3. Okay? Then what do? Well, this means that x is equal to the square root of 7/3, or x is equal to the negative square root of 7/3, because if you square this, you still get 7/3. Negative times a negative is a positive and all that. So the square of this is 7/3, the square of this is 7/3. Clearly there are two solutions, and we don't want to forget that. If you had a higher power, like you have x to the 4th equals 7.3, then you could say that x equals the 4th root of 7.3, or x equals negative the 4th root of 7.3, or x equals 7.3 to the 1/4, or x equals negative 7.3 to the 1/4. Okay? And I put parentheses around the 7.3. It's not really necessary. If I don't have the parentheses there, remember that minus 7.3 to the 1/4 does not mean the 1/4 power of negative 7.3. If I don't have the parentheses there, the rules of your order of operations still tells you that the 7.3 has to be raised to the 1/4 power before you apply that negative sign. Just another little reminder. Common pitfalls. Absolute value equation. If you have absolute value of 5x minus 2 equals 3, what's that mean? Okay, well, one thing it means is 5x minus 2 is 3. Because if 5x minus 2 is 3, then its absolute value is 3. The one thing that people forget is that if 5x minus 2 is negative 3, its absolute value is the absolute value of negative 3. It's still 3. So that 5x minus 2 equals negative 3. And then we get our solution. In this case, x equals 1, if I did it right in my feeble head. In this, x equals negative 1/5. And check my solution, check my arithmetic. Okay? Now, sometimes you'll have an equation of mixed type, like a power function equal to an exponential function. What do you do then? Well, like you have 3x to the 5/8 equals 12 times 1.4 to the 5x. Okay, what can you do with this? Well, you could try taking the logarithm of both sides. That would get the 5x out here where you can operate on it. But then you'd have a log of x over here. And usually, hopeless to solve by algebra. So graph each side. Okay? So, now I would first divide both sides by 3, so I'd have x to the 5/8 equals 4 times 1.4 to the 5x. I'm not going to try to do a very accurate graph of that, but x to the 5/8 is going to pass through the point 1, 1. So put 1 here, and it's going to look quite a bit like the square root function, because the 5/8 power is pretty close to the 1/2 power, and the 1/2 power is the square root. Now 1.4 raised to the 5x. Okay, what's that? Now I'm just going to graph the 1.4 raised to the 5x. And we're going to find that we don't get a solution, but we'll see. Okay, so 1.4 to the 5x has a graph that don't want to go into all the details, I'll just say them. You're taking the 1.4 to the x function and compressing it by a horizontally, squeezing it into toward the y-axis by a factor of 5, and then you're multiplying that by 4. So what you're going to have is a function, but by the time x is equal to 1, is equal to about 5.6 times 4, about 25. So by the time you get out to 1 here, you're way up here. And the graph of the function is just a graph of a typical exponential, but okay, well, I'll just graph. Okay, this would be 1.4 to the 5x. And this is your x to the 5/8. Now if I do 4 times 1.4 to the 5x, I didn't make a very good choice of a function here. It's going to go through the x-axis up here, or the y-axis at y equals 4. Okay, it's going to have a graph that looks like this. The graphs don't have an intersection point. Now, if you were able to graph both sides and find that it looks like they have an intersection point, or more than one intersection points, you can say, okay, a sloppy graphical approximation tells me we should have a solution around x equals whatever, okay? Because you would look for points where the graphs cross. At those values of x, wherever the graphs cross, the functions then would be pretty close to being equal, you would hope, if you got a good graph. Or in a case like this where it's obvious the graphs of the two sides can't possibly intersect, you say there's no solution. There's no value of x that makes this side equal to this side.